All right. So we talk about hydrodynamics of simple fluids. And I want to recap a few things because we're heading towards fluctuating hydrodynamics. So remember that we had 3 conservation laws, one for mass, the other one for momentum, and the third one for energy. And they look like so. You had the continuity equation for the mass density, where the fluxes are simply the mass fluxes. We had the momentum conservation, where we use the rho vi as the momentum, right? And this then has a form delta k sigma ik equal to 0. The sigma ik is the stress tensor. So let me write it down. For the stress tensor sigma ik, we wrote down a relation. This relation is based on our knowledge about Newton's equations and also based on some heuristics. So this term here comes from the hydrostatic pressures. This is just Newton's equations. And then we were saying that there needs to be another term coming from the dissipation due to gradients in the velocity. This is the dissipative part of that stress tensor. And I'm adding here another part, sigma ik, that's the topic of today. This is the noise part, the fluctuating part, the Langevin stress that we have in our system. Okay, and for sigma ik prime, remember we made an ansatz saying that this is linear in the gradients of the velocity. So we made a linear response ansatz. And finally, we had the energy conservation law, where we had the divergence of some current that relates to the energy, and that also needs to be conserved. And in that context, we introduced another important relation. We were assuming on heuristics that there is some heat flux, and this heat flux is a thermal coefficient, kappa, and it's proportional to the gradient in the temperature known as Fourier's law. And here as well, we need to account for some noise. So let's call this noise here vector eta. That's the noise for the heat flux. Okay, and then one important relation that we showed during last lecture is that the total change of entropy is an integral over the volume, and then we had this dissipative part of the stress tensor multiplied by 1/2 times the temperature, and here the symmetric part of the velocity gradient. And then we had a part that looked like so. This is the heat current, component I, 1/t² di t. I could also write it differently by putting the 1/t² into the derivative, but that's how we write it now. Okay, and that I emphasized has a structure which corresponds to the general Onsager structure, which says that the total change in entropy is some sum over A. Here the sum over A is an integral over the volume. And then we have this analogy between currents and their conjugate variables. So JA are the irreversible fluxes, and XA are the thermodynamic forces that are conjugate to these irreversible fluxes. Okay, in our case, in our special case, we do have a map for these irreversible fluxes. We can just read them off here from the analysis. So the irreversible fluxes are the sigmas. So sigma IK prime is one of those fluxes, as you can read off there. And the other one is J, well, let me take this with an index, JQI. So we have as the fluxes, stress, and heat flux. And then we can read off the conjugate variables. They are then 1 over 2 times T, right, dI Vk plus dk Vi. This is corresponding to the stress. And the other one, right, if I pull in the 1 over T squared into the derivative, I get the gradient of 1 over T. And this is then, did I do this right? That's 1 over T squared dIt. Okay. Okay, those are the corresponding thermodynamic forces. Okay, there's supposed to be a minus here. Good. Now let's go back here and think about the general structure a bit more. So let's go back to the general scheme of irreversible linear thermodynamics. Which I always called Onsager's theory because he made major contributions. And there, let me recap what the structure is. You had the continuity equation, or the balance equation, better to say, for the entropy that contains a temporal derivative of the entropy density and then a gradient divergence of an entropy flux. And this is general, right? And we know what this is for the hydrodynamics of our simple fluid, but let's now say this is a very general case that we study where we always have this kind of structure. On the left-hand side, you have fluxes. On the right-hand side, you have sources. Okay, so these are the sources that give rise to dissipation in our system. And we say that these are positive because we want to be consistent with thermodynamics, where entropy production is always non-negative. We do linear theory. Okay, that's another important feature. And you see in a second why that's important. And we have local thermodynamics, meaning all these quantities like temperature, chemical potential, entropy, etc., they have their local analog. The entropy production term, from what we just read for the hydrodynamics of a fluid. And in general, you can always write it that way, is a structure that's always a combination of the thermodynamic forces and the associated fluxes, as we saw it just a second ago. And now linearity means that I'm assuming that all of these currents, they are linear in the thermodynamic forces. So I write this as minus sigma b L A B X B. Okay, when you combine this, then what you have here for the entropy production, you have that sigma S is then a bilinear form in the coefficients L A B X A X B, and that then gives rise to the positive definiteness of LAB. Okay, and remember that in our general setting, we also had LAB is given by the corresponding parity of the fields that we study times LBA. That's the Onsager-Casimir reciprocity relation that we have. Okay. I hope I have this right. Now, what those currents here are is defined by this here, but how they appear in the equation of motion, we learned is different. We had the currents appearing in model A just as a derivative of the free energy, and in model B, and here also in the discussion of hydrodynamics, we had them appear as currents that correspond to the right-hand side here where you have the conservation laws. So as you compare, let's say for this case here, there's really this one-to-one analogy between this general structure and that general structure. And you see this also in model A, you see this in model B, and this is a general scheme that you have. Okay, what you can also show now, and I don't do this because I've done this for the case of let me write it here on the right-hand side. So if we look now at the noisy part, so we now ask about the thermodynamic consistency of the whole thing. And that means beyond the fact that entropy grows, we want that the equation, including all the fluctuations, converges to a Boltzmann distribution. So in that context, then, you need to extend what we had here in terms of the linear relation between the thermodynamic forces and the currents. So in addition to that term here, you need to add a noise term. Okay. And remember what we did when I introduced Onsager theory in simple ways, where I wrote down a Langevin equation, basically assuming local relaxation. There I showed you that the coefficients that appear in the correlation function of psi A are related to LAB. So when we have here psi A of t, psi B of t prime equals to NAB delta t minus t prime. There I showed you that this NAB needs to be the same as 2 LABT. Yeah.
So we kind of, from our fluid hydrodynamics, we diagnose what are the currents and what are the forces. And in model B, they came from functional derivatives of some entropy functional, right? They were spatial gradient functional derivatives. So can we write down an entropy functional for this entire theory?
Yeah, I mean, it's a different kind of reasoning. So in the hydrodynamic formulation, what you do is you base your analysis on a momentum-conserving, energy-conserving, and mass-conserving dynamics, and then it naturally comes out as we explained it to be with all the different terms for entropy, production, etc. In model A or B, we took a bit of a different perspective. The perspective we took there is that we have a thermal heat bath, and there is no real conservation of momentum in that context.
Okay, I thought because of this gradient structure of continuity equation structure of model B, this was actually designed to be a stochastic model of conserved quantities, which I thought this was the case.
No. You will see. Today we'll also study interacting Brownian particles, and then you will see how you can actually account for the fluid dynamics explicitly, where you have then momentum transferred to the fluid and back. While here, in the case of model B, when you study the system, you're basically assuming there's dissipation of that into the system. Okay? You'll see this in a minute, maybe after the break.
Is there any way to know when the source term is zero?
They are related to the Onsager coefficient. And if the Onsager coefficient have certain symmetries, then we showed, remember, in our first chapter on this non-equilibrium thermodynamics, that there are certain cases where the parity is negative, and then these Onsager coefficients vanish. Okay? But they're always one-to-one related to these coefficients here. And I think I did this here. Okay, this is for even parity. And for odd parity, we had an analogous relation. They're zero then. Good. So that's the general structure, and you can always show that. That's always true. And I spare you the algebra for that. It's really the same as we did before. You just need to rewrite this in the same way as there for the two different cases of dynamics where the dynamics is driven either locally or by gradients or some other structure. Good. Now let's apply this to our present case, to the fluid case. And there I'll show you explicitly how this works. Okay, so let's do that here for the heat flux. In the simple fluid. I could also do it for the stress tensor, but then the algebra is just more complicated. Okay, so it's actually very straightforward. So let me do that. So what you have is that check my notes. So what we have is that the heat flux, the component I, is Fourier's law plus some noise. Okay, but I need to write this in a form that actually defines the Onsager coefficient for our case, and the Onsager coefficient for our case is not kappa. Okay, because if you look at that structure, it's that combination that appears here. The current here has to be written in a linear form. So let me rewrite this such that it becomes evident what the Onsager coefficient is. So this is kappa t squared delta ik 1 over t squared dk t plus eta of k. of k. Now you see I have written it such that this is a function of the corresponding conjugate variable. And now I can read off the corresponding Onsager coefficient. So L I k for the heat is kappa T squared delta I k. And that now means that the noise correlation function for the heat has this structure where the prefactor is 2 times kappa times T squared delta I k delta x minus x prime delta T minus T prime. So it's quite important that you always write the non-equilibrium thermodynamics here in terms of these conjugate variables, because only in these conjugate variables do you have this particular fluctuation-dissipation relation that then gives you the noise correlation with the amplitude being the Onsager coefficient of the dynamics. You can do the same thing for the momentum flux noise, and I just give you the result and you will do the corresponding algebra in the problem sets. So there, Lijkl for sigma. This is now really writing sigma ik, sigma ij, sigma kl average is this matrix times the delta functions. And that turns out to be eta times t delta ik jl. It's a bunch of indices here that I need to get right. Delta I L delta jk plus zeta minus 2/3 eta temperature and then the Kronecker deltas of ij and kl. All right, so that's what you do get for the noise correlation of the stress tensor. And it's always the same kind of logic in algebra that you need to do when you want to construct something that's thermodynamically consistent. All right, now I promised you to go to a case where the particle picture, the fluid picture, the model B, and the hydrodynamics actually meet. And this will be the chapter that I call diffusive particle systems. What I mean by that is the following. So think about particles, and for simplicity, these are small spherical particles. Yeah?
I still have a question to the part before.
Yeah.
So we had our hydrodynamic theory,
Yeah.
and today we introduced noise to it, so it became a statistical field theory, right?
Yeah.
But I don't see yet the purpose of why did we have to do this? Like, is there an experiment which we couldn't explain with the old theory?
No, it's even stronger. If you don't have noise, you will have no probability distribution function.
True, it is completely deterministic.
Exactly. And if you want to have something to approach a thermodynamic equilibrium state, then you need to have that as t goes to infinity, you have a Boltzmann-Gibbs distribution.
But this would be like a functional distribution, right? It is like p is equal to e to the minus some functional of the velocity field, or
Of all of it.
of all those fields.
Yeah.
And the temperature you wrote down there
Is the temperature of the system.
of this functional distribution, right?
Yeah.
But there's also a temperature field here, which we derive with respect to spatial coordinates. That's not this temperature.
That is the temperature that you have when you describe the system as it is off equilibrium.
That's the temperature field.
Is a temperature field that will depend on x and t, and that temperature field will converge to a constant temperature in the long run.
Which then is supposed to be this scalar T, which we use in the functional.
Yeah, exactly. That would be the temperature that describes the equilibrium steady state.
Okay. And is this kind of where we're getting to derive this functional steady state distribution?
We're not going to go there. It's just the point that it must exist. Whether you can calculate or not is a different thing.
Probably that goes to the question, can we write down the entropy functional, which maybe is a similar thing that the free energy functional, right?
Yeah, at the moment, you have those functionals. They exist, they are there, and they constrain the structure of the equations. Here we even know them, right? So here the temporal change of that is given by the right-hand side. We know what the sources are, we know what the corresponding quantities are, and for the simple fluid, I have calculated everything, and you can just use it to study the full dynamics of a fluctuating hydrodynamic problem. It's complicated, right, because it's a nonlinear problem. There's a lot of things that are still open, but you can do it based on the equation.
So all those little fluid elements which flow where we get those field theoretic thermodynamic quantities, we don't describe them with noise at all. Like those are kind of deterministic or black box thermodynamic systems, and now this collective.
Okay, so
add the noise.
Yeah, you need to add the noise because otherwise you don't get a probability distribution function. That's the point.
That's clear.
Yeah. And for model A was really, really obvious, right? Yeah. Because there it's e to the minus beta times the free energy functional that we use to define the theory. Here it's kind of less obvious how you get this in the end, how this would look like. But it's always the same thing. You want the system to ultimately relax to thermodynamic equilibrium, because otherwise the theory you're writing down would not converge to a thermodynamic state. And a theory that lacks noise will have some dynamics, but the dynamics will at the end show a steady state. Let's say it has a steady state, which is fully deterministic. And that's why you need the noise.
Okay, so the philosophy is if I look at a bucket of water, it's actually like a thermodynamic state, not a deterministic.
Yeah, in fluid dynamics, it's not that relevant, I would say.
That's why is this complicated?
It's just a matter of principle that if you were to measure hydrodynamic fluctuations, which you can, then you would need to do it this way and complement the theory by these kind of Langevin noises.
Okay, right.
And I take the case of a fluid because it's really the paradigmatic case that combines different aspects. It combines the conservation laws that we saw. It combines that the fluxes are not just chemical potentials. The fluxes are also heat fluxes. The fluxes are also stresses that generate that. And when you now look at a much more complicated many-body system with other elements that play a role, then these features that we saw in the simple fluid, they will appear also. Okay? That's why. It's the simplest case, despite the fact that it's actually quite complicated already. Okay? Good, now let's go there. Maybe things become even clearer when I study that. So here I have particles, and they're suspended in a fluid environment. And if you now say you just have a single particle and look in a fluid environment, it performs Brownian motion because the fluid acts as a heat bath with all the collisions. That's the basis of the Langevin theory that we constructed. And if we just say that, then the medium that these particles are in is serving the purpose of providing friction, but not providing momentum transfer. Okay? And let's look at this first. So you can either say this is a dry system or a wet system, which basically means that you consider Brownian motion with damping, or you take the fluid serious. And we will do both. I will start with that case first, and then after the break, we go to the wet system. Okay, so let's start with the dry system first. And let's say we have a free energy functional for our density of these particles. So rho of x and t is the particle density of our Brownian entities here. And let me write this down. This is a space integral over all space. Then it has a term which is simply the ideal gas term. So rho log rho minus 1, that's an ideal gas entropy term, nothing but that. And then you can also add and say there is another term that comes from pairwise interactions, where I now need to integrate over x and y, and the densities at x via a pairwise potential interacts with the particle density at y. Okay. You can approximate that. So for the case that the potential that we have here is short-ranged, you can Taylor expand inside, right? You can define here a variable which is the distance, and then expand around this distance here, and then do a Taylor expansion in V. And this then gives you a free energy of the following form. This is dx. And then you will have some kind of local part. And this local part that you have here will contain a term T rho ln rho minus 1. That is just the entropy term that we already had. And then from the Taylor expansion, the leading order term will give you something proportional to rho squared. And I call the prefactor here chi over 2. This is related to an integral of the pairwise interaction potential. And on top of that, there will be here a term coming from the second order Taylor expansion of this interaction term, and that will give rise to a gradient rho squared term. So you see you get the same kind of structure as we had for model B for this free energy in the case that the interaction potential is short-ranged. All right. Now, what do? We now assume a dynamics which is, it's an assumption. Okay, we assume, and this is where the dry part comes in, that the density, well, that's not an assumption. This is what's always true. This is just a conservation law. For the mass density, the assumption comes now. The assumption is that the current that I have, I take as a term which is a Onsala coefficient that depends on density times the gradient of that free energy functional with respect to rho. Plus a term that comes from the noise. So I have some kind of noise term that we call lambda of x and t. That's a vector. And it has an amplitude, which I just naively take to be determined by the fluctuation dissipation theorem. So 2 times temperature times L of rho. the lambdas are white noise. That's equal to delta alpha beta delta x minus x prime delta t minus t prime. Okay, so local relaxation into the free energy minimum by chemical potentials that drive the currents in that case. So there's a few things that need clarification here. One is, what is L of rho, and how do we fix it? Is it a constant, or is it a function of rho? If it is a constant, then there is no ambiguity in what you write here as the Langevin noise, because then the Langevin noise that you have is additive. If there is a density dependence of L, then you have multiplicative noise. And you know, we discussed this quite at length, it's not clear a priori what kind of interpretation you should choose. So I'm telling you now, without showing you the proof, but it's in my notes, that if you have L of rho and you want that P of rho of x equilibrium is proportional to e to the minus beta f of rho. Okay, so if you want this, the system's supposed to relax to thermodynamic equilibrium, then the interpretation you need to use is the one that was introduced by Peter Henge. So this is the interpretation where instead of Ito as Platonovich, you have, so to say, the opposite end of the discretization. In Ito, you take it before the noise. In Henge, you take it after the noise. And in Platonovich, you take it in between. Okay? And this is quite important, that this interpretation that Henge came up with is needed for thermodynamic consistency. Otherwise, the system does not relax to thermodynamic equilibrium. So maybe that answers part of your question. So for that case, you need the noise, otherwise you don't even get a probability distribution function. All right, now let me come to the choice of this L of rho. Okay, the key thought here is the system should reproduce Brownian motion also in the case of no interaction. So if V is 0, then one should recover diffusion, meaning that dt rho of x and t in the deterministic limit is d nabla squared rho of x and t. So you require that the macroscopic observation that particles show diffusion, if they're non-interacting, that should be recovered. Okay, so let's see what this is. If we take diffusion only, if we want diffusion only and no interaction, then the only part that comes in the free energy functional is the one that comes from entropy. All the other terms are due to interactions. So for that case, our chemical potential, which is the derivative of the free energy with respect to rho, is simply the log of rho, and here I take just the ideal part of it coming from the entropy. So chemical potential is log of rho. That means that the gradient of the chemical potential, which is really this quantity that comes in here that drives the current, is, well, the gradient of rho over rho. Well, and then when you look at the equation, if you want that to be the case, then the 1 over rho here has to actually cancel out. Otherwise, this won't work. Okay, so that means, oh, I should be more careful than that. No, it's right. So, because this is the current, is the coefficient times the chemical gradient of the chemical potential, and then the equation is the gradient of that current. Okay, so we have here L of rho must be d times rho. So we do have a kinetic coefficient that does depend on density. And therefore, when we go back here, there is an interpretation issue. And as I told you, you have to use Henge's in order to get an equilibrium distribution. It also gives the same thing as the calculation which I didn't do for you, but which I noted during a lecture, coming from interacting Brownian particles, where you use Dean's approach and use delta functions to derive this. What we found there is also that it goes like the square root of rho. And the way we argued is square root of rho makes sense because particle fluctuations are like square root of the number of particles in a given domain. So a noise that scales like the square root of density makes perfect sense. However, in the Dean-Kawasaki approach, what you get is not really a density. You get something that refers to delta functions. And there the interpretation was Ito. Okay? So that means when you do coarse graining from this Kawasaki approach, and I don't know really how this works, you should actually recover, when you do the coarse graining properly, that the real interpretation for density fields that you can actually measure in a coarse grained sense, the interpretation has to change to the Henge interpretation. Otherwise, the whole theory is not thermodynamically correct. Good. Now, maybe we stop here and have some questions, then we continue with the wet case after the break. Questions?
So the wet case is where the fluid from the hydrodynamics comes in.
Yeah.
So far there's, well, it could come in via the V, right?
So right now the fluid is in there. Remember, diffusion coefficient by Einstein-Stokes relation is related to the viscosity eta. So the fluid comes in, it gives rise to this Onsager coefficient, but only in the sense that the fluid is providing a dissipative environment.
Yeah. So the velocity of the fluid for those equations,
it's not a variable that we consider. And after the break, I will show you how you then combine this with the simple hydrodynamics approach that we had, Navier-Stokes equations, and how that is consistently integrated in a system where the Brownian particles affect the fluid and the fluid acts back on the Brownian particles, and the whole thing is then a momentum-conserving dynamics.
So this rho is some sort of the density of test particles which we put in the fluid.
You can really think of the particles themselves. So really,
this is the same rho we had before.
It's the same rho you have before. It's the density of plastic beads, colloidal particles, proteins in a fluid environment.
So basically the hydrodynamics, which models the rho as a statistical field theory, we now try to model with this 1B approach.
This is a hydrodynamics in the sense that we use coarse-grained variables. It's not a hydrodynamics in the sense that it's fluid dynamics.
Okay, so
there's a distinction. Okay, when I talk about hydrodynamics, I mean a much more general framework. I mean that you can represent the dynamics of a complex many-body systems in terms of density fields, velocity fields, and other tensor fields or vector fields. That's what I call hydrodynamic approach.
okay.
Hydrodynamics specifically for a fluid means what we had here, it's gone, in terms of the density, the momentum, and the energy, and the corresponding Navier-Stokes equations.
Okay, so basically here we're not just trying to describe the simple fluid anymore.
No, not yet.
But we will.
We will. So right now, the background is a simple fluid. And this background as a simple fluid in the dry case has an eta, which is the shear viscosity. And by Einstein-Stokes, you have a relation between that eta and d. So I say it again, the environment is a dissipative environment where damping happens, but in a way that the momentum is dissipated into the fluid environment.
So in the wet case, we see transport of the velocity field.
Yeah, and then we need to again go back to a formulation where we have stress tensors, and then we need to argue what kind of stress tensors do we have, and how do they interact between the fluid and the colloidal particles.